To calculate the kinetic energy, we take 1/2 times the mass in kilograms times the velocity squared in meters per second. So in order to do simple conversions like the one shown above, we have 3.80 times 10 to the 4th joules, and we're converting it to calories. So we start out with the number given, 3.80 times 10 to the 4th joules, times the amount of joules in 1 calorie, which we find from our chart. And by having joules on top and bottom, we get them to cancel out, leaving us with our answer of 9,082 calories. Formulas used to calculate the internal energy include delta E equals E final minus E initial, delta E equals E products minus E reactants, and also delta E systems is equal to negative delta E of the surroundings. To use an example for delta E, we will use C plus O2 equals CO2. In this case, CO2 would be our products, and C plus O2 would be our reactants. In this case, we would take the internal energy of CO2 minus the internal energy of C and O2. According to the first law of thermodynamics, the change in the internal energy of the system, delta E, is the sum of the heat transferred Q and the work done, W. Now we will use the equation we just learned to solve a problem. Since the work being done on the surroundings is negative, the heat released by the system will also be negative. Now if we subtract both our Q and W, we will get delta E. We previously calculated delta E based on given values of Q and W. Now we will turn to calculating heat and work based on changes in temperature and volume. The first equation shows Q equals the mass times specific heat capacity times delta T. The mass will be found in grams, and the specific heat capacity will be found in a chart, and delta T is the difference between temperatures, which will be calculated by using final temperature minus initial. Based on the formulas we have just learned, we will try to use them to find Q. Based on the current information given, we can conclude that our mass is 3.10 grams of copper, and our delta T is found by taking our final temperature subtracted by our initial temperature, equaling 45 degrees Celsius. We were able to find the specific heat capacity of copper by looking it up in the chart in our textbook. We now use the equation Q equals MC delta T to plug in our data. Take note that the sign of Q is positive, and this is because of any absorbed heat from the surroundings. Now for this problem, we are given the same information, except this time we are given Q and not given temperature final. In this case, we rearrange the formula to solve for temperature final. Sometimes the mass is not directly given. In this case, they give us liters and density. If the density is given in grams over milliliters, you must first convert your liters to milliliters, then times that by the density. This will give you the correct mass to use in the equation. You then plug in the rest of the data as we did in the previous problem. The correct units for the answer of this problem will be in degrees Celsius. We will now use our new equation to solve for W. We first solve for delta V by subtracting volume final by volume initial. This will give us delta V in liters. In this equation, it equals 1.75 liters. Using the equation W equals negative P times delta V, we plug in our data. Our pressure of -1 atms times the difference in our volume of 1.75 liters equals -1.75 liters times atm. For this problem, our answer needs to be in the units of joules. Going back to the conversions we learned earlier, we know that 1 liter atm is equal to 101.3 joules. With a quick conversion, we have the correct answer of -177 joules. For this problem, they want us to solve for delta E of the reaction. Based on the information given, we are going to do a three-step process based on the equations we just learned. The correct units for the answer for this problem should be in kilojoules over moles of table sugar. Our first step is finding delta T by taking temperature final subtracted by temperature initial. We now have all the information to solve for Qcal. We now take our Ccal of 4.90 kilojoules per degree Celsius times our delta T of 3.41 degrees Celsius. Our degrees Celsius cancel out, leaving us with Qcal equals 16.709 kilojoules. We then need to find the negative Q reaction by using Qcal equals negative Q reaction. Our Q reaction is negative 16.709 kilojoules. Now to find delta E, we must put Q reaction over the number of moles used in the problem. The Q reaction that we just solved for, we will put on the top of the equation. To find the number of moles used, we will times the 1.010 grams that was given to us in the equation times the molar mass of the substance at 1 mole. You find this atomic mass by adding up the atomic weight found on the periodic table for each element. So delta E of the reaction is equal to negative 5.66 times 10 to the third kilojoules over moles of C12H12O11. In this problem, we will be solving for Q by using delta H reaction. Since we are first given the amount of propane used in kilograms, we must first convert it to grams. After doing a conversion, we have 13,200 grams. We then take our mass used and divide it by the molar mass of propane to get the number of moles used. We then multiply the number of moles used by delta H reaction. Since only 1 mole was used, we will put 1 mole under the reaction. Our final answer for Q is negative 6.119 times 10 to the 5th kilojoules. Based on the given information for this problem, we are going to solve for delta H reaction. To first start solving for delta H reaction, we are going to have to go back to our old formula and use Q equals MC delta T. We first solve for delta T by subtracting 32.8 by 25.6. This gives us 7.2 degrees Celsius. To find our mass, we take our 100 milliliter solution and multiply it by our density. This gives us 100 grams. Our specific heat capacity was given to us in the problem at 4.18 joules over grams times Celsius. We then plug in our data and solve for Q. Our Q solution is then converted into Q reaction at negative 3,456 joules. To solve for H reaction, we put our negative 3,456 joules over the number of moles used. In order to find out the number of moles used, we take the 0.158 grams of Mg that was given to us and divide it by its molar mass. The correct units for our final answer will be found in joules.